Hello, I'm Nicole Fry, and this is my Physics Lab 1 constant velocity. So the purpose of this lab was to observe the concept of constant velocity through the motion of an object moving at a constant speed and direction. What I did is that I took a video of a soccer ball rolling across a flat surface of a desk as my model system for observable constant velocity. I used a program called Tracker to identify and quantify the movement of the soccer ball as it progressed in the positive x direction, and through this program, I obtained the ball's position at each corresponding point in time. Then I used GlowScript to program a computational model that describes the constant velocity observed using iterative techniques that utilize the principles of Newton's second law. I was able to create a simulation based off of my VPython code that accurately depicted Newton's second law. I took both the data of the observable positions and times, whether that was from Tracker, and also the expected positions and times, which was from GlowScript. And what I did is that I plotted the data side by side for analysis. Through analyzing the data, I concluded that the computational model is not completely accurate since it does not account for the force of friction acting on the ball as it moves across the surface. Here you can see a screenshot of my video uploaded onto Tracker, where I mapped the position of the soccer ball as time progressed. The program plotted the data on a table as well as graphically and serves as our observable data for the lab. I set the axes on the video to where the ball is traveling in the positive x direction. This is important because I needed to choose an accurate coordinate system in which to describe the motion of the video, or aka the soccer ball. If the axes were flipped, the signs of the position and velocity would be inverted, and the points would be reflected over the x-axis. Additionally, someone who is looking at the data would think that the object is moving in the y direction, not the x direction. After I ran my video through Tracker and got my position versus time data, I compiled the necessary data to describe the translation of the ball in the next portion of the lab. In order to use Newton's second law, I needed to know the initial velocity of the soccer ball. I calculated this by taking the first position time point and second position time point and plugging them into the formula velocity is equal to displacement over delta t. My initial velocity vector ended up being 1.8 meters per second in the positive x direction. I also noted the mass of the ball, which was 0.43 kilograms, and the first and last position time points. This information is necessary to use Newton's second law in the code to get the computational model. Here are screenshots of my code that I used in order to make my computational model for the second portion of the lab. So although we were given starter code to work with, there were a couple changes that I did make to the code in order to fit more accurately what I was supposed to be doing in this lab. So inside the while loop that we're using, there's a line of code ball.vel is equal to ball.vel plus fnet divided by ball.m times delta t. So this line of code updates the ball's velocity through the iteration using Newton's second law, which tells us that the final velocity is equal to the initial velocity plus the net force divided by mass times delta t. And then the ball's position is equal to the ball's position plus ball.vel times delta t. This updates the ball's position through each iteration using the formula the final position is equal to the initial position plus velocity times delta t. Additionally, there was a line of code that was t is equal to t plus delta t. This is basically used to advance the clock per se. This updates the time as we iterate through the loop. And then lastly, the net force was equal to the vector of 0, 0, 0. Here's the computational model I created with my code of the expected data for the ball's movement. As you can see on the position versus time graph, the slope of the line is increasing and at a constant rate of change, meaning that this model is telling us that the soccer ball is experiencing constant velocity. Now that I had both data sets, one that pertained to the observable motion of the soccer ball and one that pertained to the expected motion of the soccer ball in terms of constant velocity, I took both data sets and I plotted the data sets into Excel to create a linear graph that plotted each data set side by side in order to use for comparison and analysis. So So the computational model accurately shows the motion of the soccer ball when the net force acting on the ball is equal to 0. Because a side-by-side graph of both data sets align, meaning the slopes appear to be equal, for a segment of the time elapsed, the graph shows that the soccer ball appears to be moving with a constant velocity since the change in time is so small. Realistically, however, there are frictional forces acting on the ball that are not accounted for but are depicted in the data shown by Tracker. This explains why the observational data given by Tracker experiences a slight decrease in slope. The results of the lab show that the ball is not traveling at a constant velocity, which is why it does not mirror the predicted motion calculated by Newton's second law, and therefore helps us conclude that the computational model is not completely accurate. Additionally, it's important to note that Newton's second law only has F net in the equation and does not have any additional information about the number of pushes and pulls, which would mean that it would be not very realistic or maybe even impossible for you to say how many pushes and pulls are added together to give 0 net force in the case of where I was observing the soccer ball. Thank you for listening.